So I leave you with all those different models. We won't talk all of them. We won't kind of use all of them in the practicum section, but just since they span different areas of data, if you have different types of data, you'll probably have to use one or the other. So it's good to kind of know about them and what they're used for. In practice, when you want to train these deep learning models, they're as Abhi, I think, mentioned, there's something called overfitting and underfitting, and this I kind of just show what this looks like. So on the right here, we can see that when you have a regression problem, you're trying to learn these points. Underfitting may be just like, okay, here's a single line, and it tried, but it's not doing that good. Whereas overfitting, your line may be very jagged. It's actually like memorizing some of the points. And in some ways, we don't really expect the true distribution to be this zigzaggy. We actually expect it to be this like parabola. So the noise, your model is so good at representing things that it's starting to represent the noise as well. And so that's overfitting. For classification, we get the same issue. You have these outlier points. And so because your model is very flexible, it's learning the outliers as well. And it's going to make the model suffer in that it will be not as good at generalization. Whereas, to get it just right, we actually have to ignore some of these outliers. And underfitting, we just, we haven't really gotten that good. In deep learning, a lot of times because these are very high dimensions, we don't have these nice 2D things to look at. So all we really have to go by to figure out if we're overfitting, underfitting, or have it right is by the loss training and validation curves. So the symptom of overfitting is that your validation curve has plateaued. So your training keeps going down. So your model thinks it's getting better. The loss keeps going down on the training data, but on the test data, it's not getting any better. In some cases, we don't see it here, but I'll show an example where the validation actually starts getting worse progressively, even though the training data is getting better. And what we want to see is this, where they're both going down together. It's inevitable that your training data will be somewhat, like your model will be somewhat better at reconstructing the training data, but we don't want it too much. And there are a number of ways to address this, but typically it involves just rethinking how you approach the problem, changing the network architecture, sometimes playing with the actual hyperparameters of the training, like the optimizer, the atom. And other times it just is like, fix your data. Think about this classification problem where we have all these outliers. There could be a problem with the data. Your data normalization could have a problem to cause this symptom. But yeah. So here I've added a cheat sheet because deep learning involves a lot of math to know what is going to converge well. So what's used in practice are the following choices. So typically nowadays for the hidden layers, So each of the models has, the input layer. You have these several layers in between things, and then you have an output layer. So for hidden layers, everyone nowadays is using ReLUs. So unless you read a paper and they prescribe some very specific hidden layer activation, ReLU seems pretty good. It performs well, and it works good for very deep networks. But for output layers, we have it really depends on the type of model you have. So if you have a regression problem, you typically will have a linear output layer. That is, you do nothing to what comes out, and its domain is from negative infinity to infinity. So you can kind of fit to any function. And then the loss function you would use for a regression problem is a mean squared error, or MSE. And this will just, on every dimension, square the error between what you predicted and what it actually was. For classification, though, you'll want to be using, for binary or multi-label classification problems, a sigmoid activation function and a binary cross-entropy loss function. These are just based in math, so this binary cross-entropy is using entropy. It's minimizing the entropy, and this is what the math says. These things are provably, going to converge. So if you use MSC and you're trying to fit to a sigmoid, you can end up with issues. So if you want a classification problem, then you need to use kind of these losses and outputs. And finally, for multi-class, we'll use a softmax activation function and this other loss function called categorical cross-entropy. So, I mean, these are like good rules of thumb. I wouldn't deviate from them unless the paper prescribes some very specific loss function. Uh, you know, and as before, where we talked about scikit-learn being a one-stop shop for machine learning, like library. So there are two major libraries in Python for machine learning, for deep learning rather, and they are TensorFlow and PyTorch. They are very popular, and allegedly PyTorch is a little bit more adopted in the research field, but TensorFlow, which is made by Google, is also very popular and often used in, I think, enterprise more, but both are completely capable of being deployed to production, and both can be used. It's really a personal preference by this point, and these continue to evolve, and both of them kind of learn from each other, and they continue to get better. The practicum that I'll show is actually in TensorFlow, but again, easy to translate to PyTorch. And so I'll conclude this lecture part. So we talked about feed-forward neural networks, autoencoders, GANs, and transformers. I guess CNNs as well. That's in the next section. So yeah, in terms of models, we talked about those. We talked about these different embeddings, and how embeddings are very useful for taking data in a particular domain and making them kind of suitable for a feed-forward neural network for an NLP. And those embeddings include CNNs for images, word2vec for text, and attention for kind of sequences of things, whether it's text or something else. We have Then we talked a little bit about some of these practical concepts, like how gradient descent works, under and overfitting, and various loss and activation functions you can use for training different types of deep learning model outcomes. And then, of course, the TensorFlow and PyTorch.